All right, let's continue our discussion about Laplace transforms. So in part one in class last week, we introduced a Laplace transform and some of its properties and a table in which was very helpful for us to see some basic forms. So from part one discussion, recall that the Laplace transform of a function in terms of t, most of the time this Laplace transform is transforming functions with the variable being time, is equal to this integral where s is a complex number, and recall a complex number has a real part and an imaginary part, where both a and b are real numbers and I is the imaginary number. The Laplace transform is particularly useful in solving linear differential equations, such as those arising in the analysis of electronic circuits. There's also a lot of engineering applications as well. So today we want to introduce the theorem about inverse transforms. So last class we were using a table very similar to this one, but we were taking the Laplace transform of the function to get this formula that we filled in to give us the result. But now we're going to go backwards. We're going to be given the result and we're going to take the inverse to get us back to the original function. So without further ado, let's do some examples so we can see how this works. So our first example will be finding the inverse Laplace of 1 over s to the 5th power. So let's see, I can do it right on the PowerPoint for this one. For these two first examples, and then I'll have to switch to our whiteboard as they get longer and bigger and crazier. So for this Laplace transform, if we looked back at the chart to find which one of the formations matches this 1 over s to the 5th, then I would go with the Laplace inverse of n factorial over s raised to the power of n plus 1. Okay, and according to the table, it says that this particular Laplace inverse gives us a result of t raised to the nth power. So if we take a look at what we're given, Laplace inverse of 1 over s to the 5th power, and we start to break this down to fit the form of this this setup that's in the table. Then I take this and I look for what n would be. So if you see this, s is raised to the n plus 1, and we see that n plus 1 comes out to 5. So I'm looking at an inverse transform of s to the 4 plus 1. And then that means that n is 4, so my numerator is going to be 4 factorial. Now 4 factorial, remember, factorial means to multiply 4 times every number below it until you get to 1. So 4 times 3 times 2 times 1 is 24 over s to the 5th. So that's not going to work, right? Because we have an original problem that's 1 over s to the 5th. So how do I fix the fact that in order to use this form in the table, I need to make this a 1? Well, it's a similar concept to what you guys learned when you were integrating. Remember when we had to put in a constant in order to make an integration rule work, we always had to balance the equation by putting the complement, or the reciprocal rather, on the outside of the integral. So same thing applies here. We will multiply by 1 over 4 factorial to balance the equation, and that is 1/24 times 24 gives us 1. So that solves our numerator problem. So overall, we get an answer of 1 over 24 times t to the 4th is our original function for this 1 over s to the 5. Let's take a look at the next example. So our next example is taking the Laplace inverse of 1 over s squared plus 7. So again, you look back at the table to see if you can find the closest match in the table. And for me, I'm looking at the Laplace inverse of b over s squared plus b squared. Okay, and the table says that that relates to the function sine of bt. So again, we have to be a little creative to manipulate the b and the s. Well, the s variable is straightforward, but the b, we have to try to make it work where the numerator will be a 1 and in the denominator, the b squared is a 7. So we have a Laplace transform of 1 over s squared plus 7. Laplace inverse. And we need, again, to manipulate the b. So if we think about it, let's start with the squared first. We need b squared to be 7. So we got to bring back your mathematical brain and think, well, what can I square that will give me 7? And it's probably simpler than you thought. We're going to make b the square root of 7. So we have s squared plus, if we make b the square root of 7, then when we square the square root of 7, we get 7. So I started with what I thought was the harder part. I started with the b squared because I figured that would be much more helpful for me to be able to get 7. And then the 1 on the top, well, since I set b to be square root of 7, that means our numerator is square root of 7. But if we look back at the original problem, we need it to be a 1. So we'll apply the same concept and multiply by 1 over the square root of 7 in order to balance that part of the equation. So our overall answer becomes 1 over the square root of 7 times sine square root of 7t is our function that we would have started with. Now for our next example, it gets a little funky. And if you recall from Calc 2, partial fractions is not going to be a small thing. So let me switch to the whiteboard to do this one. And let's dive in. So we're being asked to evaluate the Laplace inverse of s squared plus 6s plus 9 over s minus 1, s minus 2, s plus 4. So this is a case for partial fractions. If you recall from Calc 2, we learned partial fractions, or at least it's one of the special topics. So it is possible that you didn't get it. So here we go. We're starting from scratch if you haven't seen this before. So for partial fractions, we are going to set our fraction here, s squared plus 6s plus 9 over s minus 1, s minus 2, s plus 4. And we're going to split it up where there's some numerator a over the first product piece of the product in the denominator, plus, with no assumptions, some other numerator b, s minus 2, plus c over s plus 4. Now recall from partial fractions that the numerator is set based on the power in the denominator. So because our power on the s is 1 is why our numerators are all constants. If we had an s squared, then we would have to make our numerator ax plus b. So you always go down 1 from what is presented in the denominator. So now what we want to do is we want to multiply by the common denominator all the way across the board. So we're multiplying by the s minus 1 times s minus 2 times s plus 4. And if we do that, then what we get is s squared plus 6s plus 9 is equal to, and we get a times s minus 1. Let me write smaller, I'm going to need the room. we have a times s minus 1, s minus 2, s plus 4, all over s minus 1. And notice that the denominator is missing on the left side of the equal sign, but that's because if I multiplied by this whole denominator on the left side, it just cancels the denominator. So that's why we no longer have a denominator on the left side. So plus b times the same common denominator all over s minus 2. Then we have plus c, same thing. Let's see if I can squish it in here. Minus 1, minus 2, s plus 4, all over s plus 4. So our denominators canceled on the left side. Pieces are going to cancel on this right side, leaving us with s squared plus 6s plus 9 is equal to a, and we're going to have to multiply this out. So we get s squared plus 4s minus 2s, so that gives us plus 2s minus 8, plus b times, if we multiply s minus 1 times s plus 4, we get s squared plus 4s minus 1s gives us plus 3s, and negative 1 times 4 gives us minus 4, plus c times s squared minus 2s and minus 1s, which gives us minus 3s plus 2. Okay, so now that we have this equation, our goal is to find a way to solve for a, b, and c. We want to know what those numerators are. Because once we get those, then we can really work with the Laplace transform. So we're trying to break this down into a form that fits the table, because originally that form is way too complicated, and there's nothing like that in the table. So what we want to do now is we want to distribute the a, the b, and the c into these parentheses. So it's going to get a little lengthy, but we have s squared plus 6s plus 9 is equal to as squared plus 2as minus 8a plus bs squared plus 3bs minus 4b plus cs squared minus 3cs plus 2c. Now what we want to do is we want to group pieces together based on their s term. So all the s squareds are going to be grouped together. All of the s terms need to be grouped together. And all of the constant terms will be grouped together. And you'll see very shortly, if you haven't done partial fractions before, why we're doing that. So this gives us the left side of the equal sign, not changed yet. We're not using it to change it. So here we go, s squared plus 6s plus 9 is equal to, and we have a plus b plus c are all the coefficients of s squared. 2a plus 3b minus 3c is the s terms. And we have negative 8a minus 4b plus 2c for all the constant terms. Now, if we look at the left side of the equation, we see that there are coefficients to each one of these terms. Now, because we are equal, that means that the s squared term, its coefficient must be equal to the same value as the left side of the equal sign in order for the equal sign to hold. So that means this expression here, a plus b plus c, which is the coefficient of s squared, needs to be equal to 1 because the coefficient on the left side is 1. So our first equation is A plus B plus C is equal to 1. Second equation is the coefficient of S, which needs to be equal to 6. So we have 2A plus 3B minus 3C is equal to 6. And lastly, we have negative 8A minus 4B plus 2C is equal to 9. Easiest way to solve this is to use our calculators. So in the TI-89, you can also go to the Wolfram Alpha website. They also have a calculator. If you go to Wolfram Alpha, Google it and click on the Wolfram Alpha site, the calculator is on the front page and you can type the same syntax as an 89 and it will recognize what you want it to do. So what you want to do is you want to use the solve command, okay, which I believe is under F2. I don't have an 89 in front of me, but I'm pretty sure it's under the F2 menu. So we're going to solve, and you are going to enter in these equations. Oh, I did. It is under F2. I have it here. Okay, so under F2, select the solve command and enter in these equations. And then press enter and your result will be A is equal to negative 16 over 5. B, that's a 16. B is equal to 25 over 6. And C is equal to 1 over 30. So what did we just find? We found that s squared plus 6s plus 9 over s minus 1, s minus 2, s plus 4 is equivalent to negative 16 over 5 over s minus 1 plus 25 over 6 over s minus 2 plus 1 over 30 over s plus 4. So now that we've broken down this very complex fraction on the left side here into 3 less complex fractions, we can also divvy up the Laplace transform and apply the inverses from the table. So we get that the Laplace inverse of s squared plus 6s plus 9 over s minus 1, s minus 2, s plus 4 is equal to negative 16 over 5 Laplace inverse of 1 over s minus 1. Okay, so you can take constants out just like you could in an integral, plus, that is supposed to be a plus, plus 25 over 6 times the inverse Laplace transform of, whoa, here we go, 1 over s minus 2 plus 1 over 30 Laplace inverse of 1 over s plus 4. And if we look in the table for all those, we will get a final answer of negative 16 over 5 e to the t plus 25 over 6 e to the 2t plus 1 over 30 e to the negative 4t as our final answer. Let's try another one, just like that one with partial fractions. So example 8, it says that we want to evaluate the Laplace inverse transform of s over s plus 2 times s squared plus 4. Okay, so we recognize this as partial fractions because when we look in the table, we see that there is no match for this particular setup. So it means we need to break it down into something more basic or simpler. So s over s plus 2 times s squared plus 4 separates to a constant numerator over s plus 2 because the exponent on s is a 1, plus bs plus c over the s squared plus 4 because the exponent on the s is a 2. So you have to do every kind of term below a squared term, which is b times s plus a constant c. Now it's possible that sometimes the b or the c will be 0 because you didn't need both parts, but we would rather have more than less to make sure we have everything we need in the end. So again, we're going to multiply by the common denominator. So we get s is equal to a times s plus 2 times s squared plus 4 over s plus 2 plus bs plus c times s plus 2 times s squared plus 4 all over s squared plus 4. Again, that means all our denominators will cancel. And we're left with a linear, or I shouldn't say linear because we still have a squared in there, but it's a one-liner. Everything's on one line, no more fractions. And we follow the same process of doing this out. So we have s is equal to as squared plus a 4a would look better, 4a. And we have to do some distributing here. So we get bs squared plus 2bs plus cs plus 2c when we FOIL that out. Grouping our squareds, s's, and constants together, we get s is equal to a plus b s squared plus 2b plus cs plus 4a plus 2c. Again, we are lining these up with the coefficients on the left side. The only thing on the left side is the s term with a coefficient of 1, which means all the other ones are set equal to 0. So here, this is the only one that'll be set equal to 1. Both of these will be set equal to 0. They're not 0, they're set equal to 0. I'll show you. So we get a plus b, which was the coefficient of s squared, is going to be equal to 0. 2b plus c is the one equal to 1. And 4a plus 2c is also equal to 0. Using our solve command in either Wolfram Alpha website or TI-89, we get a comes out to be negative 1/4, b is equal to 1/4, and c is equal to 1/2. So we get the complex fraction of s over s plus 2 s squared plus 4 is equivalent to negative 1/4 over s plus 2 plus 1/4 s plus 1/2 over s squared plus 4. So then the Laplace inverse of this complex fraction that was difficult to solve without breaking it down becomes negative 1/4 Laplace inverse of s plus 2, or sorry, 1 over s plus 2, plus 1/4 Laplace inverse of s over s squared plus 4, plus 1/2 Laplace inverse of, these are all supposed to be squiggly brackets, of the last part, which is 1 over s squared plus 4. Now we have to do a little bit of manipulating for this last one. So if you look into the chart, remember for this one, the chart was b over s squared plus b squared. Well, if we rewrite this 4 as something squared to recognize what would b have to be, it would be 2 squared, right? So we don't need to do that square root thing because we got 2. This 2 squared is 4. Square root of 4 is 2. But remember, the numerator needs to be that b, and the b is not 1, the b is 2. So this somehow needs to become a 2. So in order for this to be a 2, I'm going to multiply by 2 and compensate on the outside, just like you would do for an integral. If you needed an extra constant, you just multiply by it and provide the reciprocal on the outside. So that's going to give us a coefficient in front of this last Laplace inverse as 1/4, because we have 1/2 times 1/2. So overall, we get negative 1/4 e to the negative 2t. Again, the e to the negative 2t comes from the table, plus 1/4 cosine of 2t. And this last one, again, is a 1/4 because we had to compensate. We have the 2 1/2s being multiplied, and it comes out to sine of 2t. All right, let's head back to the point to discuss some more Laplace transform. So we can also do transforms of derivatives. And the Laplace transform of a derivative is given by the integral from 0 to infinity. It's very similar to what we just worked with, except you can see that the function here is the derivative. And if you work this out, we can use something a bit simpler, which is this formula here, this s with times the function of y of s minus y of 0, where this capital Y is actually a fancy schmancy letter used, but we'll just go with capital Y because it's easier to write. Okay, so 3-step procedure for solving linear differential equations using Laplace transforms. You take the Laplace transform of both sides of the differential equation. You solve the transform for the y of s function, and you find the inverse transform of the ys to get the function y of t, the solution. So here we are. We did some practice with Laplace transforms in the table last class. We've just entertained the Laplace transforms inverse table, and now we are applying all of what we just learned to solve a differential equation. So let me switch over to that whiteboard again. And let's do 2 examples. So example 1 is to use the Laplace transform to solve the initial value problem. And our initial value problem is dy dt plus 3y is equal to 13 sine of 12t, where the initial value at 0 is equal to 6. So let's do this step by step. Step 1, we take the Laplace transform of both sides. So we're taking the Laplace transform of the derivative plus 3 times the Laplace transform of y. Again, notice me taking out any constants. They're unnecessary to be in the transform. Is equal to 13 of the Laplace transform of sine of 12t. Step 2, to apply these Laplace transforms, as we just saw on the last slide, the Laplace transform of the derivative, it boils down to something simple, which is the sy of s minus the initial value. Okay, so that's that part, plus 3 times the Laplace transform of y, which the Laplace transform of y is y of s, is equal to 13 times 2 over s squared plus 2 squared. Oh, wait, hold on. Let me double check if the example is supposed to be a 12. No, it's supposed to be a 2. Okay, so that's a typo on my part. I was going to say that doesn't make any sense. So this is supposed to be a 2, which makes more sense. So there was an error in my notes, so I'll fix that so I don't make that mistake again. There we go. Okay, so the 2 in the sine function is what's b, And if you look at the table, you can see that. And so we have b in the numerator, and it's 4 here, but we write it as b squared. Or actually, it's b squared, which is 4. All right. So now let's simplify some more. So this sy of s minus okay, let's actually let me do this in red. So here's an y of s term. Here's another y of s term. So let's put those closer together. So sy of s plus 3y of s. Now the initial value here, okay, so minus the initial value, we're going to put that here. So that's minus the initial value of 6, and then equals 13 times 2 over s squared plus 4. So let's group the y of s terms. So that gives us s plus 3 is the coefficients of the y of s, minus 6 is equal to 13 times 2 is 26. Next step down, let's move the 6 to the other side of the equal sign, because remember, we're solving for the y of s function. So we have s plus 3 times the y of s function is equal to 6 plus 26 over s squared plus 4. And now what we want to do is solve for y of s by dividing by that binomial s plus 3. So we get the function y of s is equal to 6 over s plus 3 plus 26 over s squared plus 4 times s plus 3. Joins the other denominator. Now, if we add these together, which in order to do that, to put this together, we will have to find the common denominator. So I'll have to multiply top and bottom by s squared plus 4 on top and bottom. We're adding fractions, common denominators. And so you have 6s squared plus 24 plus 26 all over, okay. There. All over s plus 3 times s squared plus 4, which gives us 6s squared plus 50 over this common denominator. So now we're looking at this function and we're trying to solve, but we see that we have a complex fraction going on here. So that's what tips me off to say, okay, this is a partial fractions problem. So I'm moving on to partial fractions. So you're starting to see all the pieces that we practiced prior to this example now being put together to solve a differential equation. So we have partial fractions gives us 6s squared plus 50 over s plus 3 times s squared plus 4. We break it up into two denominators, the s plus 3 and the s squared plus 4. So this first one, s plus 3, has an s to the first power, which gives us a constant numerator, while the s squared gives us that bs plus c. And we follow the same process. We multiply by the common denominator. So we get s squared plus 50 is equal to a times s squared plus 4, because the s plus 3 canceled with the denominator, plus bs plus c times s plus 3, because the s squared plus 4 canceled with the denominator. So you see I'm moving a little faster now because we've done two partial fraction problems already. So now we multiply out 6s squared plus 50, as squared plus 4a, plus bs squared plus 3bs plus cs plus 3c. We group by s squared, s, and constant. So we get a plus bs squared plus 4. Oh, no, just kidding. That is a constant. So s terms, 3b plus cs. And our constants is 4a plus 3c. Matching them up with the coefficients from the left side, we get that a plus b is equal to 6, that 3b plus c is equal to 0, and 4a plus 3c is equal to 50. Now you put that into your calculator or Wolfram Alpha with the solve command. And what comes out is that A is 8, B is -2, and C is 6. So we replace that back into this equation here with A as 8 and B as -2 and C as 6. Okay, let's write that out. So we now have that y of s is equal to 6s squared plus 50 over s plus 3 times s squared plus 4, which we have broken down into 8 over s plus 3 plus -2s plus 6 over s squared plus 4. So now we're at step 3 where we are finding the solution. So y of t is equal to 8 Laplace inverse of 1 over s plus 3 minus 2 Laplace inverse of s over s squared plus 2 squared plus 3. You know what, let me put this, I'm not gonna have enough room, let me put it underneath. Plus 3 Laplace inverse of 2 over s squared. Well, you know what, let me start with what it looks like originally. 6 over s squared plus 2 squared. But in this last one, again, we're gonna have to do a little bit of manipulating, because if you look back in the table, with this s squared plus b squared one, you have to have b in the numerator. So we have to make this 6 a 2. All right, what happened to 6 to get 2? Well, we divided by 3. So technically we multiplied by 1/3 to get 2 from the 6. So we have to multiply by the complement on the outside, or the reciprocal rather. This time we multiply by a fraction inside. So we need to multiply by the whole number on the outside. So we multiply by 3. Oh, and you know what? That's where that 3 came from. Sorry, that 3 didn't belong there. That was part of my my compensation to get that 2. So a 3 comes on the outside of this last one in order to multiply by 1/3 inside to get that to fit the formula in the table. So altogether, we get a solution. Y of t is equal to 8 e to the -3t minus 2 cosine of 2t plus 3 sine of 2t. And again, where is this sine, cosine, and e function coming from? If you look back at that table, you will see that those are the functions that correspond to these setups. Let's try one more example. Last one, let's solve a first order initial value problem using the Laplace transform. The differential equation is dy dt minus y is equal to 1 with the initial value y of 0 is equal to 0. Step 1, take the Laplace of both sides. So we have the Laplace of the derivative minus the Laplace of y is equal to the Laplace of a constant, 1. Step 2, the derivative becomes the s y of s minus y of 0. The Laplace of y becomes y of s. And we know from last class that the Laplace of a constant is 1 over s, or the constant over s, which our constant is 1. Okay, let's group our y of s together. So we have s minus 1 for the y of s functions, the s from here, the negative 1 from here. The minus the initial value, our initial value is a 0, so minus 0. I'm just emphasizing it, but it's going to go away. All equal to 1 over s. So we get, if we solve for y of s, we get 1 over s times s minus 1. Now, again, we see that there is a product in the denominator, which is complex. So we are going to do partial fractions again. So we have 1 over s times s minus 1 is equal to a over s plus b over s minus 1. Both the denominators have an s to the first power, so we only need constants in the numerator. Multiply through by that common denominator, and that gives us 1 is equal to a times s minus 1, because the s canceled with the denominator, and bs, that sounds really bad, but bs, because the s minus 1 canceled with the denominator. 1 is equal to as minus 1a plus bs. Grouping together, we get a plus b for the s term, minus a for the constant. Our s term on the left side does not exist, which means the coefficient was 0. So a plus b is set equal to 0. And our constant term, negative a, is equal to the constant on the left side, which is 1. So we solve for a, we get a is equal to negative 1. This one's faster to do out by hand than to put in your calculator. If a is negative 1, then what does b need to be in order to solve this equation? Well, b is equal to 1. So we put this all together and we have the function y of s is equal to 1 over s times s minus 1, which we found with partial fractions is negative 1 over s plus 1 over s minus 1. So step 3, to find the solution, y of t, we get negative Laplace inverse of 1 over s plus the Laplace inverse of 1 over s minus 1, which gives us the final result of negative 1 plus e to the t. So some of them are much simpler. The last one that we did with the solving the differential equation definitely was a lot longer. But you can see that Laplace transforms. It is still a process, but we can solve some complicated, especially complex fractions in a much simpler way than if you tried to attack the problem in any other way. All right, well, this concludes our second part of our introduction to Laplace transforms.